All right, so it's been a while. Loki, we're gonna make some problem videos. God dang it, man! I've been so unproductive. Um, it's June 6th. It's still not even that far in the summer, so I want to change my productivity. Um, yeah, I'm looking at my Discord right now. That's actually not ironic as we speak, but yeah. So I'm going to be going over this question called infinite set, and it's a pretty nice problem. We'll just get straight to it. So it's basically this, right? Um, You're given an array consisting of n distinct positive integers. Okay, so distinct, I guess, is pretty important here because they bolded it. And the idea here is that there is a infinite set called S, and basically the way that you populate values in that set is you're either a member of the initial array given to you, so all those values get put in the set, and then to generate more values, you can either just double a number and then add one, or you can quadruple a number, and that's how you like generate different numbers in the set. And we're curious to find the number of elements in the infinite set S that are strictly smaller than 2 to the p. And because this number is going to be arbitrarily large, we're going to modify some arbitrarily large prime, which is 10 to the 9 plus 7. So then you realize that the two integers they give you are n and p is ridiculously big. So obviously you can't brute force this and just generate all the numbers strategically, because 2 to the 10 to the fifth is ludicrously big. So that obviously would not work. So then you also have your values, they're 10 to the 9. Okay. So what's interesting here is the first observation. Like when you're thinking about problems, you need to think about what's special about this problem, right? Like there's a reason why they're saying find the number of elements smaller than 2 to the p. Um, like that should guide you in some sense, because another thing to make problems simpler or to reduce problems is by thinking of other ways to rephrase the question in a more straightforward manner. This is a very nice technique. It's really helpful when you're trying to reduce the complexity of problems. So there's this one observation that kind of honestly gives it away, but it's a little tricky and a little subtle. So you have to realize that when they say find the number of elements in S that are strictly smaller than 2 to the p, you can rephrase this as find the number of elements in S whose binary representation is no more than p bits long. So what I mean by this is let's say p is 2, right? So we have 2 squared. We want to find all the elements that are less than 2 squared. Well, 2 squared in its binary representation is this. So basically, if you want to find all the elements um, that are less than 2 squared, it's equivalent to finding all the elements that have no more than 2 bits in their binary representation. So like 0, 0, 0, 1, 1, 1, these are all those elements, right? And so that's the idea, right? In general, if you have 2 to the p, then you know that p1s is basically the smallest number or the biggest number that's smaller than 2 to the p, because 2 to the p is basically just one is just 1 and then p zeros after it. That's basically what 2 to the p is. And so basically the trick in this problem is to think about the numbers in their binary representation, and it's honestly very tricky. It's honestly a very tricky observation. um, and you see why this is nice, because again, it reduces these it simplifies these operations, because if you think about these numbers in their binary representation, then if you double a number and then add 1, it's equivalent to just slapping 1 to it in its binary representation. For example, if I double, so 5 in its binary representation is 101. If I double 5 and add 1, it goes to 10. And doubling any number in binary in its binary representation is equivalent to just adding a 0, right? You're just shifting the bits left. And when you shift the bits left, then each value just takes up 2 times its original place value, and therefore the entire sum, when you add it up, would be multiplied by 2. And so in this case, if you double a number, you add a 0. And then if you add 1 to an even number, then it's equivalent to just replacing that 0 with a 1. So effectively, the second statement here, or the first operation type, is just slapping a 1 to the end of a binary string. And similarly, with 4y, if you double a number like 20, right? So it's like 1, 0, 1, then it's just adding two zeros, right? Because it would be 2 to the fourth, and that would be 2 to the third, and or the 1, 2, 3, 4, 5. Wait, what? Oh yeah, 2 to the squared, sorry, and that would be 20. So there you go. You've simplified the conditions. It's basically just operation 2 increases the length of a number in the set by 1, and operation 3 just increases the length of a number in the set by 2 in its binary string. And obviously operation 1 is just you're a member of the array, because you obviously need to start with some values to be able to populate the set infinitely. And so yeah, the idea here is that you think about these numbers in their binary string, and it reduces all the fluff in the question, because obviously when they say less than 2 to the p, you have to think about what's special about 2 to the p. And what's special about it is that it has this nice you can the 2 to the p condition allows you to reduce the problem in that way. So it is really tricky, but I think it's just you got to be a little creative sometimes, right? So the way that you actually code this is that the problem is hella reduced now. It's just basically saying, so what we can do here to solve this problem is we can let dp of, so this is really not, it's a really basic dp, let dp of I, this basically represents um, the number of elements who have I bits in their binary representation. And yeah, and with the assumption of DPI is that we've already calculated 0 to I minus 1. And if we've already done that, with the base case just being like 0, and that's obviously just 0, then we realize that if I know this, then it's very easy to transition, because either I can come from an element that is I minus 1 bits long and just slap a 1 to it by using operation 2, and that's going to be dp I minus 1, or I can use operation 3 and look at all the elements that are I minus 2 long and then just slap two zeros at the end of it, or I can use operation 1, which is basically just finding all the elements in the set that have I bits in their binary representation. So count I, and count I is basically just the count of elements in A that have I bits long. And then you just basically run this for loop from 0 to n. And obviously you might be a little bit careful with these edge cases like 0 minus 1, but that's pretty much all you do. And then you can add, basically you can go from 1 to p and add all the dp values up. So it's basically just dp of I, and I ranges from 1 to p. And that's basically your answer. And so this technique of like sort of break counting them at like fixed lengths and then adding all the values up is a pretty standard technique. So there's not much of motivation there. It just helps you reduce, like simplify things, right? So then we can. There's a little bit of okay. So you might think this is it. There's a little bit of a problem though of overcounting. So if you look at this second test case, you can realize that you can actually go from 5 to 20 by quadrupling it. And so if you actually run that DP in, it's kind of funny because I messed that up a lot. If you actually run that DP, then you're going to overcount because of the case that there are numbers that can intersect paths. So 5 and 20 can intersect paths because you can get from 5 to 20 by quadrupling it. So what we need to do is we need to make sure that any two numbers cannot intersect paths. So what we do to fix this is it's pretty easy. You sort the numbers. Actually, I said it's pretty easy, but I got cooked. But you sort the numbers from least to greatest, and you start with the smallest number, and you basically say that if the number is odd, you subtract 1 and you divide it by 2. And then you check if that element is in the set, and if it is, then we don't need that number. If the number is even and divisible by 4, then you divide it by 4. And if that number is in the set, then we don't need it anymore. And so basically, you can just, and you know that dividing by 2 and dividing by 4 are generally quick. 10 to the 9 is like 30 bits. So therefore, for every element, you're going to apply like log n operations on it at most. Therefore, it will be like n log n to make sure that no two numbers intersect pat. And once you do that, you can apply the standard DP on the problem. And so take you to the code. So basically, what we're going to do is we're going to take A. And once we take A, we're going to sort it from least to greatest. And then we're going to go from least to greatest, and we can say, well, temp is greater than 0, because you don't want to keep dividing this infinitely, right? We can just say if it's divisible by 4 and the set contains that number divided by 4, then we don't need it, so we're not going to add it. But if it's an odd number, and then we subtract it by 1 and then cut it by 2, and it's in the set, we still don't need it. And if that number is not contained in the set, then clearly this is a useful number. So we're going to need it. So we can just break. We can if it doesn't have any number, then we don't need it. We can just get out of here. We can just get out of here and then add the number, because it will be useful. And then we can just do the DP, where DP of I just represents all the numbers in the set that have I bits and their binary representation. And the first thing we need to do is we need to populate DP with already the numbers in the array. So we go through the numbers in the array, we count the amount of bits they have. And that should take like n log n. I just looped from 0 to 30, and I just checked if I can just count how many bits a number has in its binary representation. Only takes like 30 operations, so like log n, and then we just say dp bits plus plus plus, right? And then we just slap on our formula, and then just keep it running some, and then be aware that you do need to mod this. So I have a nice template, so I don't have to worry about modulo. It is actually really nice. I hate worrying about that. So there's a second thread template. It's actually not mine, but it's second thread. So he does all this mod stuff. You don't have to worry about that, and then you can also have mods set to the value that they want. So yeah, that is it for the videos. We just have a nice little problem there. Yeah, see you guys later.